Welcome, this is question 4 for AQA's June 2013 past paper. This is obviously Unit 2, as I mentioned. This question is all about Hooke's law and proportionalities, etc., and other things that go along with it. Okay, so I've not even bothered trying to attempt to properly draw this graph, properly labelled partly because, well, I can't be bothered and you can look it up online. So if you are doing this question from the actual exam as some kind of homework or whatever, or if you're actually just doing it for revision off your own back, which, you know, is really good. Okay, so as I said, what I would ideally want, if you don't want to print all the paper off, but you are doing the paper, this is one of them questions, just for the graph really, that you have to kind of print off. You should really print this off, because of the method that I'm going to be going through it. Now I will obviously go through in one or two methods where you can kind of count it off the screen. Obviously you can do that really, rather than print it off, but it's better to print it off essentially. Anyway, you already know that. Okay, so the first one, part A. Now I'm not going to write this down. Actually, it just says state Hooke's law. Now you could, what I did in this question, because it's worth 2 marks, I actually talked about it. So I said, Hooke's law states the force applied to extend a spring from its unstretched length is directly proportional to the extension of that spring from its unstretched length. In other words, F equals K times delta L, and then you would say, okay, well, F is the force required to extend it to a certain length, delta L is the extension from its unstretched length, and K is the spring constant. Now, realistically, you could just state the equation and label what each of the bits of the equation means, really. So that's what you could do. Or you could do what I did and talk about it. It doesn't really matter. Okay, so this next question asks us, I don't know what my computer's doing there, asks us to calculate the spring constant for this, obviously, spring. Now, we know F equals K times delta L, so we've got F on the y-axis and delta L on the x-axis. So the gradient is obviously the force over the extension, which if we use this equation that we stated in part A, should get us this spring constant. Now obviously there's no point trying to work out the gradient over past A, because at this point A, we need to follow it where it's following Hooke's law, so that's up to point A. I mean, I've not drawn it ideally right on there, but point A is really where the limit of proportionality stops, okay? Where the limit of proportionality is, which is, as I said, you need to look up on that. But it's just the point up to which a wire or a spring stops following Hooke's law, okay? Right. Okay, so it's just a case of working out the gradient. Now, what I would do is say, okay, well, K is equal to F over delta L, so therefore it's obviously the gradient. Now, what I did was 30 newtons over, so a difference of 30 newtons over 0.026 metres, okay? And that got me 1,154 newtons. Now, as with all of these questions in AQA where they ask you to work out the gradient, there is a marginal percentage for error. Not too big, but obviously not too small either. They've allowed a plus a 6 variation on either side, so plus or minus 6. So obviously it's in the range from 148 to 160. Okay, so it's a range of 12 obviously. Okay, so if you got any of that, any in between there, you would get the full correct answer. But I mean, personally, as you were going through the exams, as long as you get the gist, you just need to be a bit more accurate if you didn't get quite inside that range. But as I said, that's quite a generous range, really. Okay, so that's part B out of the way. It's quite, as I said, so far it seems a nice, easy question. So far, it says. Okay, so part C says, use the graph to find the work done in extending the spring up to point B. Okay, so work done is also known as the energy transferred, and the energy transferred in a graph like this is the area under the graph. So what it's asking up to point B. So we draw down from point B, and all this area here is the work done in extending it up to that point. Okay, so what you could do is split that up into a triangle and some other weird shape, and try and work out the overall energy stored by, which is the work done, which is a half times F times L, delta L, or a half times K squared times delta L, or do, which is much more simpler. Now, the area under the graph, because it's force times distance, essentially this distance is defined as length, but means kind of the same thing. A force times distance is the work done, because that's work done. So you can kind of see where we come from that. So therefore you just work out how much one square is worth. So one big square and one little square, whichever you're doing. I pick one big square, and that's just whatever value is here, whatever the width of the big square is, whatever the height of the big square is, times them together to get the value of one square, which I worked out to be 5 newtons times 0.005 metres, which gets you 1 square is equal to 0.025 Newton meters. Okay, and you work out how many squares there are, which is 35 whole squares and 16.5 squares, which gets you 35 whole squares and 16 half squares. If you total it up, that's 43 squares. If 1 square is worth that, we know there's 43 squares, so you just times it by 43, obviously. You times by 43 squares, you should get 1.1 joules. Okay, remember this is energy, because it's work done, it's measured in energy. Okay. Alright, so hopefully that makes some kind of sense how we did that. I'm just looking at, I'm assuming they're going to give you some boundaries on this as well. Okay, so is it so what it says on the mark scheme is any line from B to a point on the y and the x-axis from 0.005 to 0.020. Okay, it doesn't really give much of a guidance. You should get something like 1.1 joules. Okay, so as long as you get something in that area, you should give yourself the 2 marks. Okay, so now we're going on to 4F. 4F says, 4D. So 4D says beyond point A, the spring undergoes plastic deformation. Explain the term of the meaning plastic deformation. Well, anything that's plastic, when you try and bend it, it deforms. Because if this, trying to build it up, so if you didn't get it straight away, if you get it straight away, then you can skip a little bit, which I'm sure you would do anyway. Plastic deformation, you just think, okay, well, it's the deformation of plastic. So what is that? Well, it's when you bend plastic so much. When you bend plastic, it just goes really white and snaps. Okay, it's kind of the same thing when we get to this plastic deformation point, which is just really what you because when you bend that plastic and break it, you can't. When you bend it and it goes white, it can never be the same length or shape. Okay, so when you make a spring undergo plastic deformation, same kind of things happen. Okay, just the essential is you can't. It's permanently extended. Okay, it's the words that you would use for that. Can't be put back to its original length. Okay, 4E. When the spring reaches an extension of 0.045 meters, the load on it is gradually reduced to 0. On figure 6, sketch how the extension of the string might vary up until 0. Okay, so okay, right, sorry, there is a range on 4A, but I'll go back to 4C, sorry, but I'll go back to that in a minute. Okay, so it's just a line from point B on the x-axis from 0.005 to 0.20. So basically, wherever 0.45 is, I think it's at A, it just looks something like that. So it can't go back to its original length, okay? Hopefully that makes sense. Now, this one before, this 1.1 joules, okay, there was a range for that. What I just said when I was trying to explain 4C, I was actually saying the explanation for 4D. So I do apologise, but as I said, all of this is online. They would accept anything from 1.05 to 1.10, okay, if not rounded. Okay, so really that's what we're looking at. So that's 40. 4F says, without further calculations, obviously we don't need to do any maths here, weirdly enough, compare the total work done by the spring when a load is removed, when the load is removed from the work that was done by producing the load of 0.05 meters. So really, we're just comparing this area in here to this area out of here. Okay. So what you would talk about, obviously, it wants you the work. So it says the work done by the spring is the work done by the spring is less than the work done by the load. Okay. So what we're saying. The work done by the spring is the internal energy. Basically, we've stretched it out, and to cause this extra extension that is permanently there, we've put some energy that we can't get back. Okay, that could be in terms of heat, for example. So this internal energy of the molecules is what is causing this permanent extension. Okay, so what you say is the work done by the extending the spring to its full length is greater than the energy stored by producing the extension 0.045. So really, the equation they want you to, the words that they want you to say, as I said, it's only worth 1 mark. So the work done by the load is greater than the work done by the spring, which just means when we extend it to this point, because we're really considering this part here compared to this part, the work done by the load is greater than the work done by the spring. Okay, hopefully that makes some kind of sense to you. As I said, I've probably not done a great job of explaining that, but as I said, hopefully it makes some kind of sense to you. So that's the end of question 4. That's 12 marks there. As I said, hopefully that lasted a little bit. I didn't confuse you too much. I'm more than willing to have another go at the question, but as with time, I want to get through the papers, I will come back to that if needs be. And please do let me know in the comments if there's anything that you found particularly tricky with this question and you want me to just type it up, so you've always got, you have to watch the whole video again, which I'll admit is quite a challenge. Okay, so thanks for watching, and we'll see you in the next video.